So what's going on, folks? Just kind of wanted to give you a heads up. All right, a lot of you guys were saying, hey, we don't have anything due this week, and you are right. There is nothing due, D-U-E, this week. However, there are totally things to do, D-O, this week. You like that? It kind of came out with a pun like that. Anyway, let's go check out this week. I think we're on the 27th. This is the 4th week already. All right, so what is due this week? Nothing. What do you need to do this week? The stuff that is due for next week. And you got a bunch of stuff due next week. And the stuff that is due next week are killer big assignments. Like, for example, this HSA study guide, I'm going to go with you through it today. And guess what? I'm going to explain to you what they are right now, so it's not going to be that completely daunting. This HSA study quiz, I'm going to go through, or you guys can do that as well. Now, this one's a 20-question quiz. All right, so let's start off with this. What is the study quiz? You guys know that in the future, you guys are going to have an HSA, right? We're going to have an HSA coming up, and according to the plan, for the people in Hilo, it is going to be next week on the 6th, and then for the people on Oahu, it's going to be the 11th, and then for the people in Kona, it's going to be on the 14th of February. Got it? So this thing is coming up. It's not like right upon us, but I mean it's getting closer. So what I'm going to do is I want to make sure you guys study for that, and I want to make sure you guys prepare for that. What I'm making you do is I'm making you do this quiz. It's 20 questions long, and it's a pretty good one. And I want you guys to, when you do the quiz, I don't want you to just do the A, B, C, and like tell me your answer. I want you to write down why you chose that answer, and I'm asking you like additional questions. So like, is the answer A, B, C, or D? And then my next question is, what is the difference between intrusive and extrusive igneous rock? And what are some characteristics of igneous rock and sedimentary rock and metamorphic rock? Got it? So like this one is pretty important. This quiz is pretty important. You need to turn that in. All right? And where did I get this from? Well, I got this from, and I think that you're going to need yeah, okay. I got this from the HSA website. This is exactly from the stuff. In fact, this is what Nolan suggested that I do. So I'm doing that. Props to Nolan, by the way. And don't yell at Nolan for saying, oh, Nolan, you gave us a bunch of homework. No, I was totally going to do this anyway. But he just said, hey, you should have everyone go through the science worksheet. So that's what I'm doing with that. Cool? But when you submit the assignment, fill in this document that I have. Fill in the document that I'm giving you. Don't fill in just the HSA thing. You can go through it if you want, but they're not going to grade it for you. We cool? So that's the HSA study quiz. Wait, oh, what are you asking, Victoria? Because I asked, are you cool? And you said not really, but then I think you're answering Lucas and said, did I miss anything? No, not really. All right. So HSA study quiz. Now the HSA study guide. All right. Here's what I did. Okay. I wrote down. I know it looks like a 10-page document. And you guys are like, oh my gosh, this thing's gonna melt my mind. This thing is so long. Do I really have to do all of this? My answer is, I'd like you to. And why should I like you to? Because I like you guys doing a lot of work? No. Because I'm mean? Probably. But that's not why I'm making you do this. I'm making you do this so that you can get a better grade. Do I get extra money for having you guys pass the HSA? No. Do I get less money? No. I'm doing this because I care about your grade and how you do on these things. And then you ask yourself, you tell me, well, hey, Mr. Dalday, why should I even care about doing well on these things? It's not going to help me with a scholarship. It's not going to help me with a, like that's not going to help me get into college. It's just HSA, you know what I mean? It's more of a reflection on the school than anything. And my answer to that is because taking standardized tests like that, even though I don't think is always the best way to learn or the best way to test somebody, it's the way we test people. And if you can do well on the on standardized tests like the SAT and the ACT, and even in ninth grade, you're going to take this thing called the PSAT. It's like the practice SAT. If you do well on the PSAT, they'll actually give you money. I'm serious. They will give you thousands of dollars if you ace it, if you do well. They're called like the President's Scholarship and what they'll do is you do well on this test and they'll put you into a category where you qualify for the scholarship for money for college. Now, that doesn't necessarily mean they're going to straight up give you cash, but they are actually giving you cash. I actually just dropped today. I dropped $2,000 on the one class that I'm taking at UH. I just paid $2,000 right before I started taking class. If they were to give me a scholarship, that would be $2,000 that I didn't have to pay. So I'm telling you that the scholarship is actually real straight up money. Don't think of it as like, oh, it's just scholarship money. No, it's money. That's regular money. They're just giving you that. It's like getting a gift card. A gift card's still valuable. Got it? And yes, it could be money that goes into your pocket, because if I had a $2,000 scholarship that paid for my college, then I wouldn't have to put in my credit card number today for paying $2,000 for the one class that I'm taking. One class. If you take 5 classes, that's 10 grand a year. 10 grand a semester. 10 grand a semester. That's 20 grand a year. 20 grand a year times 4, because over 4 years, that's what, 80 grand? So, do you guys have $80,000? Because I just spent $2,000 on a class, the one class that I'm taking this year. So I'm just letting you know that the stuff that I'm teaching you is so that you can get good at standardized tests. Why do you need to be good at standardized tests? Because it will get you money. It will get you scholarships. If you do well on the SAT, a lot of times those are merit-based scholarships where you need to have a certain SAT score, an ACT score, or a PSAT score in order to get these scholarships. This is straight up money, folks. So, should you work hard on it? Yes, you should. Why should you do it? Because Mr. Dalday told you so? No, because it's going to help you out. That's why I'm doing this. That's why I'm so passionate about this, because I want to see you succeed. So yes, you're right. That's extremely nice in kind of a mean way. All right, and they're not even that hard. I'm asking like, what is the wavelength and frequencies? And guess what? A lot of this stuff, all I did was I took everything that you should have learned this year, everything that you did learn this year, and I kind of put it into one big assignment. And it's really just kind of like filling in the blanks, and you can use the internet all you want. You can look it up. What is it? In fact, I even tell you, use the internet and define what a P wave is. Use the internet and define what an S wave is. Of course, I'd like for you to write it in your own words as well, to kind of interpret what it means. You know what I mean? So that's why this thing looks so long and the study guide is so long. But guess what? In the lectures that I'm going to go over for the next 2 weeks, we're going to remember all of the stuff that we talked about here. So basically, I'm going to start doing your homework for you right now. Mr. Dalday, you're so cool. Yeah, I know. Sorry. I mean, it's just the way I am. So right now, pull out those packets or pull up that study sheet or just listen and take notes or whatever you want, because let's get into it. Got it? We're going to talk about waves. We're going to talk about like different frequencies and all of that kind of stuff. I'm going to show you guys all the pieces of it. All right, you guys ready? Tell me when. Go. Go. Remember to record. I think I'm recording. Pretty sure I'm recording. I hope I am. What does that say? All right, I'll tell you what. I'll double record. Am I recording on this one? Okay. I'm going to record on one computer. I'm going to record on another computer. All right, so I'm two recording. I'm recording on this computer. I'm recording on that computer at the same time. I can't really double check for the other computer to archive whatever, but we'll see. All right, participants. There we go. All right, so check this out. Let's talk about waves. Waves. You guys remember waves? Remember doing the wave? Woo! There's different types of waves. The ones we're in Hawaii, we're dealing with like ocean waves, but the actual kind of waves that we like to deal with is like sound waves or light waves, that kind of stuff. What is a wave? It's a disturbance that transmits energy without permanent movement of the particles, usually through some sort of medium. What does that mean? Well, I'll tell you. Remember when you're doing the wave in the Aloha Stadium, right? We had everyone stand up next to each other, and then we did the wave. And you stand up and you sit down. That's it. Okay? It actually transmits energy. You can actually see the energy travel along the stadium. But the actual people in that wave, did they move? No, not really. They stood up periodically. They sat down, but that's it. They didn't really move seats or anything. They just moved up and moved down. So they moved temporarily, but they didn't move permanently. Does that make sense? So the water wave would just kind of go like this. It's kind of like that, like, right? Like the robot wave or the dancing wave or however you want to call it. My elbow doesn't really move this way. My elbow just moves up and down, but you can kind of still see the wave going. You guys get it? All right, and what is it talking about a medium? A medium is basically, oh yeah, you're supposed to see me. I'm sorry. Pull up the participants thing and you guys can see the video camera of me. What are we talking about a medium? A medium is like the people in the Aloha Stadium. Because without the people, or without my arms, there is no wave. You guys get it? Like there's no wave. Right now Aloha Stadium is empty. You can't have a wave in Aloha Stadium because there's no people. There's no medium for that to transmit through. So, yeah, and you guys are like, duh. But remember I asked you this question. You guys had such a hard time with this thing. Is remember the Death Star? And the Death Star exploded? And what happened? It went but what should have happened? It should have gone. No sound. Exactly. I'll do it again for you. I mean, just in case you didn't have the camera up. Yeah, it should. It would have gone boom, but no sound. So. And why is there no sound? Because there's no medium. There's no air in space, and the air is the medium that it travels through, so therefore there is no medium. Good, exactly. Now, there are waves that don't need a medium. Sound waves do need a medium. Light waves do not need a medium. Because we can still see a star. We still get radio waves from a star. We get gamma rays from a star. X-rays from a star. And that has to travel through space. There's no air in space, so there's no medium. But certain waves don't need a medium. When we're talking about like actual physical waves, like a sound wave or a mechanical wave or like an ocean wave, you need a medium there. But some waves don't always need a medium. Got it? All right. We don't need to do that one. All right, here's the parts of a wave. And I actually hate this picture. I don't know why I'm using it. But in order to measure the wavelength, you measure it from the top to the top. We call that the crest to the crest. Say that's 10 feet. Got it? Let's pretend that's 10 feet. If the top of the wave to the top of the wave is 10 feet, what do you think the trough to the trough would measure? From the lowest point to the lowest point, what would that measure? 10 feet as well. So it doesn't necessarily need to be the top to the top. It could be the bottom to the bottom, or even the middle to, not this middle, but the middle of that. So as long as you have like two identical parts of the wave, that is the wavelength. That's the horizontal part. It's how far in between, how long this wave is. You guys get it? All right. Now, the wave height, this is why I hate this picture, is because the wave height, they actually got it wrong. Well, I always talk about the amplitude of the wave. What is the amplitude of the wave? The amplitude of the wave is not what they have here as the wave height. The amplitude of the wave measures from this dotted line all the way to the top, or this dotted line all the way to the bottom. They're both going to be the same measurement. It's from the middle of the wave to the top. That's the amplitude. And I don't know why they don't have that in this picture, but that's what they got. Yep, exactly. Hawaiian style, bro. From the middle of the wave to the very top, or the middle of the wave to the very bottom. What they have here, what they have in this picture, the wave height, is the haole style, mainland style. From the top of the wave all the way to the bottom of the wave. So if like a wave is breaking and it's 4 feet haole style, that means from here to here is 4 feet. If we're doing 4 feet Hawaiian style, that means from here to here is 4 feet. Which means from here to here is 8 feet, which means you probably would drown inside of a 4-foot Hawaiian style wave. Yes, exactly. And in science, we measure the amplitude of the wave, which goes from the middle to the top, and that's scientifically correct. Hawaiians got it right that time. Got it? Now there's different things that a wave can do, and one is called reflection. Reflection is something that you see all the time. It basically bounces off exactly as it hits. We also have this idea called refraction, and that is something a little different. You guys ever, does anyone here spearfish? Does anyone here fish with a spear? Or have spearfished? No? I don't fish. No, but my friend does. Okay, alright. Check this out. If you have a spear, and I've actually done this before, if you have a spear and you want to fish, and you know, I get the one with the rubber band and I spear it like that and I open up my hand. But if you have a spear and you're trying to spear a fish, and you're standing outside the water and you're looking inside the water and you want to spear it, you can't aim directly at the fish. Does that make sense? You can't aim directly at the fish if you're looking at a fish in the water. Because the fish isn't actually there where you see it. The fish is actually off a little bit. So you have to account for that off. And why is that? Well, it's because the light rays that you see, say that the fish is this little green dot. This area over here, say that's air, and say this area over here, say that's water. The light rays will actually bend when it hits a different medium. And that's called refraction. You see that effect here. Look at this. These are two straws. So you have the straw coming in, and as soon as it hits the water, the water is, it kind of like got shifted off. That's called refraction. The light rays are bending as it goes through a different medium. Yeah, you guys remember? Oh yeah, I remember the refraction lab. Exactly. And the difference between the mediums has to mean different densities. So apparently this block of prism or glass or whatever has a different density than this one, because as the light passes through, it bends. And the reason being is because it goes slower. The light goes slower through the denser medium, so therefore it will actually bend and it won't go as fast. Does that make sense? Now, what is the electromagnetic spectrum? Electromagnetic spectrum is really just electromagnetic wave, which includes light waves, and the difference is the wavelengths. So like if I have these wavelengths really close to each other, we're talking about maybe light waves. If I have these wavelengths big, if it's a big wavelength, then we're talking about radio waves, where it's like a really big in between. Cool? And I think that a good way to see that would be scale of the universe. Let's look at that. I like using this H-twins one. But what we're talking about here, I always think it has this spacey music. What we're talking about here is like when we're talking about radio waves, we're talking about the wavelength, and the wavelength would be from here to there. It's from the crest to the crest. That distance, which apparently is about the size of the Eiffel Tower. No, it's bigger than the Eiffel Tower. It's about the size of half of Central Park. Those are pretty big. But we can get smaller wavelengths, like for example, FM waves, which is about the size of a giraffe. Or if you shake that thing even faster, or get smaller wavelengths, like the microwave has wavelengths about the size of a penny. From here to here is the size of maybe a marble, glass marble. And we can get it even smaller, and we've got infrared waves, which is the stuff your TV remote puts out, and that's about the diameter of a skin fiber. It's way smaller than the diameter of a hair, of one strand of hair. Or you got light waves, which is about the size of your X chromosome, or your Y chromosome. And then the violet waves are even smaller than that, and that's the size of the largest virus that we have. Ultraviolet light, X-ray light is the size of, I don't know, a buckyball, which is a carbon-60. And you even have gamma rays, which is smaller than an atom. We cool? So all we're talking about is the wavelength is much smaller. And that's the difference between a gamma ray and a light ray wave, is really just the wavelength. We're talking about the distance between each crest. The gamma ray is so small that it's the distance between both of these crests is smaller than the hydrogen atom. Don't get me wrong, it's bigger than a proton, but it's smaller than an actual atom. So there we go, waves, or rays. So now all I'm asking you is tell me some facts about this. And really what I'm doing here, you know, with the study guide, all I'm doing is I'm making you build the cheat sheet that you are going to use to help you study for this test. All right, let's talk about this stuff now. Ready? P waves and S waves. Do you guys remember what P waves and S waves are? Okay. P waves are going to be the blue one, S waves are going to be the green one. Watch this video. All right, let's watch it again. All right, let's look at it. I paused the video. Let's look at it. The blue waves are out here, whereas the green waves are in here. What does that tell you? Well, no. The P waves the P waves are in front and the S waves are in back. That tells you that the P waves travel what? Slower or faster than the S waves? Okay. P waves travel faster than the S waves. They just travel faster than the S waves in general. Here, I'll bring it back for you slowly. See, look, the earthquake happened at the same time, and both the P waves and the S waves were sent out at the same time. But very quickly, you see that the P waves, or the P waves, are in front of the S waves. They just travel faster. Now, we're going to talk about this. Why is there only blue lines here, whereas why is there no green lines there? Why is there blue lines here and no green lines in this area right here? Because S waves can't travel through it. Exactly. Now, Sophia, you threw something out there, and you were absolutely correct. The reason what Sophia said is Sophia saying, "Oh, wait a second." Yeah, I say wrong because people think, "Oh, I'm correct." No, you're wrong. The reason why P waves make it through the liquid core and not the S waves don't make it through, is not because of the speed that they're moving. Yes, the P waves do travel faster than the S waves, but that's not the reason why the P waves make it through. I kind of like your thought process, but let me tell you what's going on. All right? What is a P wave? Well, if I have two particles, you can have a wave that goes like this. Boom, 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 and it gets knocked. This is a P wave. Got it? This is an S wave. If I was holding, thumbs together, I go like this. So if I move this guy up, then this guy will move too. Like that. And it kind of moves like this. Are we cool? Now, if I'm talking about a solid, then when I move this thing up, since they're connected by a solid, this will move as well, and they'll be connected. Are we cool? So if I'm talking about a solid, it will move up and this will move up. But if I'm talking about a liquid, the particles aren't attached to each other. So when I put an S wave through a liquid, this guy will move up and down, but this guy will be like, "What the heck are you doing? I'm not attached to you, I'm just watching you do something dumb." You get it? That's why an S wave cannot travel through a liquid. But in a liquid, even though they're not attached, if this guy goes boom, this guy is still going to move forward and hit the next guy. That's why a P wave can travel through a liquid. Got it? All right, and if you play this thing, what we have here is the S waves have made it already. The P waves haven't even made it to the edge. Look over here. The P waves. Why do you think these things got split up now? Why do you think it got split up? Well, I mean, yes, but the S wave, why is the S wave not just this continuous thing? Because it's going through different densities, and so it travels at different speeds. That's why this S wave is getting broken up. Even though it can travel through the core, it has different densities inside. We cool? All right, good. Then you guys pretty much can answer everything about S waves and P waves. All right. All right, let's do the wave on a string simulation. That would be this guy right here. And I only got 4 more minutes, so I'm going to go as far into this as I can, and then you can do this. So wait, I've got no end, and I'm going to have no dampening. There we go. So this is really important. Let's look at a wave. So it's going to go. I know it lags, but I mean, this is the best we got. Actually, I'll tell you what. I'm going to spam you guys the sim. You guys can open it up, play with it all you want while I'm talking about it. But watch the computer screen. All right. So here I paused it. The wavelength. What is the wavelength? The wavelength is from the crest to the crest, so from here to here. That is your wavelength. Your amplitude goes from the dotted line, the middle, to the top. That's your wave amplitude. Got it? Natalie, I will try to get a Jeopardy game going for you guys starting next, like, either next lecture or next week. All right. If you make the amplitude smaller by basically, I can make that, or I can make the wavelength smaller by increasing the frequency. So now watch. The wavelength is actually smaller because it was before it was actually 30 something, but now it's only like 18. So the distance between the troughs of the thing, I didn't change the amplitude of the wave. It still goes up to a height of 10, but as far as like going from this crest to that crest, it's smaller. And the smaller you make that thing, or basically the more you increase the frequency, which decreases the wavelength, the more you increase the frequency, that will take you to different parts of the electromagnetic spectrum. You guys remember this stuff? Is this all like coming back to you? Good. Because that's my point, is I'm trying to make sure you remember what you're doing. So a lot of this stuff I'm pulling from your old assignments. So if you can pull up your old assignments, that would be good. So I talk about wavelength and I talk about dampening, and I don't have any idea why the spoon looks cut. I'm going to change that. I'm going to actually just delete those things right there. All right, we cool? Now I'll tell you what. I don't have a whole lot of time. Actually, you know what? I'm pretty much out of time. Let's see. Can I get you guys to 12:30, or do you guys have to go to another class? All right, let's do this. Let's talk about gravity, because I didn't get to talk about this stuff. And what I'm doing for you now is this. This document that I gave you is huge. It's a big document. I admit that. I understand that. This study guide is large. But I'm actually lecturing straight from it right now. I'm reminding you about all this stuff. See, did you see my idea about how gravity was created on that one assignment? Which it was. I know, it is immensely big, but I'm actually doing your work for you right now. I mean, you still have to fill in your definition, but I mean, I told you what it is in this lecture. What's the amplitude of the wave? Amplitude of the wave is the measurement from the middle of the wave to the very top. What's the internet's definition? I want you to copy and paste what the internet says versus compared to what you say it is. We cool? All right. You guys have a huge English project? All right, then I'll tell you what I'll do. Let me think. Okay, wait. I'll tell you what I'll do. A huge social studies or a big project, huh? Alright. Here's what I'll do. Okay. You see this? You see that half of the assignment? Gone. And then this stuff down here, deleted. There. Sound fair? Alright. You still have to do the top half. I know it's a lot, but I deleted the second half of this assignment. That's my compromise. And look, I've already lectured on half of it. Cool? Alright. Let's talk about the gravity force lab. Do you guys remember what the universal equation for gravity is? So I won't have time to get to the rock cycle to remind you what that is, or the global winds, or this flash presentation. We'll get to that next time. Do you guys remember what the universal gravity equation for gravity is? I'll show it to you. Once you see it, you'll be like, oh yeah, I've seen that. Here it is, right here. Write this down. The force is equal to big G times M1 times M2 divided by, and I wrote this down as R squared last time, but they put D squared. Okay, alright, fine. They're calling it something different. The R that they mean is, I said R back then is because I'm talking about like the radius. But the D that they're talking about is the distance. That's fine, it's the same thing. It's just a different letter, whatever. So you write that down. G M1 M2 over D squared. Now, if you were, oh, what is this below the F? That's the word grav, G-R-A-V. And that's basically telling you the force of gravity is equal to big G M1 M2 over R over D squared. Now, if you were in 9th grade physics, I would actually make you use this equation and plug in numbers and all of that kind of stuff. You're in 8th grade science, so all I did was I showed it to you and I say be familiar with this. But you don't need to like know what G is. You need to understand that G is a constant. It's like the number pi, but it's just some other number. I think it's 9 times 10 to the 9th or something like that. It's a big number. M1, is the mass of one of them. And M2 is the mass of the other thing. And then the D is the distance in between them. So like, if I have a planet that has a mass M, and I have another planet that has a mass M, then the force between them would be F. But if I increase the size of this planet on the right side to be twice that mass, then the force would increase by twice. Does that make sense? If I have a more massive planet, then the force would be bigger. Yes? No? Good? Alright. Now what if I increase the distance by 2? What would the force do? Would it go... Because, like, alright, so I have a planet here and a planet here, and I make it twice the distance away from it. The force would get smaller, but by how much? I'm curious to know if you know. Would it get smaller by 2? if I have the force over here and say that the force is like 10 pounds, and then I move it over here twice as far, would it go down to like 5 pounds? I know, you're right. It does say it right there. It would go down, not if I had two planets right here and the gravity between them is 10 pounds. It's pulling with a force of 10 pounds in between here. And I take this planet and I move him twice as far away. Then the force that they're going to feel is not going to be half of the force. It's not going to be 5 pounds. The force that they're going to feel on each other is actually a quarter of what it originally was. So it's only going to be 2.5 pounds. Because if you think about it, if you put in a 2 over here in the distance, right, it's, instead of d you put 2d, then it's going to be 2d squared. The 2 squared is actually 4, and that's why it's a quarter of the force that you feel. Does that make sense to you? So that one's a little bit different, but anyway, you just know this. Here's what I want you to know. The masses are in the numerator, and the distance is in the denominator. What that means is, if I make the masses bigger, the force increases. If I make the distance bigger, the force decreases. And changing the distance has more of an effect than changing the masses, because of the d squared part. Exactly. Oh, by the way, g is apparently 6.673 times 10 to the negative 11, and you don't need to worry about that. Don't worry about what that number is. Just know, all you need to know about it is that it is a number that exists. Later on, you'll have to know what that number is. Are we cool? Convection current, we haven't talked about that one. Here we go. So I ask you, what is G? G is the universal gravitational constant. What is M1? That's the mass of the first object that you have. What is M2? That's the mass of the second object you have. What does the R stand for? That's the distance in between the two objects that you have. This is what you should be writing. I'm actually doing your homework for you. Type what will happen to Fg if you increase the mass, M1. Well, if I make M1 bigger, then the force gets bigger. Okay, don't you have class at 1:45?
Yeah. Can I just
Go talk to Mrs. Alright. Anyway, I gotta finish class. I got another person coming in. I'll talk to you guys later. What is this? Oh my gosh, Dewey. Dewey what? Dewey bye? Alright. Oh, no. I'm talking to this guy over here. He has class at 1:45, not you. Yeah, don't worry about that. All right? Have a wonderful rest of the day. I'll talk to you folks later.